Hello, I'm Alex Madonic. I'm your National Chemistry Week coordinator in the California section of the American Chemical Society. We're based here in the East Bay of San Francisco, but our geography extends all the way to the Oregon border and across the state to the Sierra Nevada, and we'd love to hear from you. So if you want to help us celebrate National Chemistry Week this week or anytime during the year, we are ready to help. You can reach me at NCW-Coordinator at sonic.net, or you can look us up at calacs.org, and that's where I'll post this video. We're celebrating National Chemistry Week this very week, third week of October, and we have activities that you can try at home or in your classroom. In fact, we've published a book celebrating chemistry in both English and Spanish. And our theme this year is fast or slow, chemistry makes it go. And we're talking about the speed of chemical reactions, and some, in fact, are very slow, like rust, and some are very fast, like fire. Even though those are similar reactions, one is very fast, one is very slow, and that's exactly the kind of difference that chemists are interested in. And we're constantly trying to make reactions go faster if we need them to. You can use a catalyst or heat. Or we can slow them down with cold. I mean, that's why we put things in the refrigerator, right? Okay, so that's our theme for National Chemistry Week, but today I'm going to talk to you about something a little different. I'm going to talk about electricity passing through a solution through water. So we're going to do some chemistry. And when we start our day in the lab, what do we do first? We put on our safety goggles. We're going to protect our eyes because if anything unexpected happens in the lab, that is the place that we are most worried about getting hurt. We're not going to take any chances. Now, I'm not working with anything dangerous today. I don't expect anything surprising to happen, but it's just like getting in the car. You put on your seatbelt. You don't expect to crash, but if you do, you'll be very glad you had that seatbelt on. So I've got my goggles. We're ready to go. I have a battery here and some lights. They're Halloween lights. And they're connected to these electrodes which are in the water. And there's a little bit of light visible flashing in these lights, but not much. And that's because water by itself does not contain many ions, almost none. In fact, the ions in this water came from the Sierra Nevada or maybe from the reservoir where there are minerals that dissolve in the water. Water by itself, pure water, would not conduct electricity, not enough for us to see it. But there is a little electricity going through the solution. It's not much, and let me show you what it would look like if I connected the wires directly. Well, it'd be a lot brighter, wouldn't it? Okay, now what is electricity? We haven't exactly said. It turns out electricity is charged particles moving. That's what electricity is. And you can see that in a lightning strike, a flash of lightning. A lot of charged particles are moving there. You can't see what's going on in this wire, of course, but there are tiny negatively charged particles moving through that wire, which we call electrons. And those were first observed in a vacuum tube by J.J. Thomson back in the 1880s. So that was the first time anyone ever observed directly a small particle that was part of an atom or molecule. That was a big discovery. It was the first time we ever found out what was inside an atom. So it turns out there are these small negatively charged particles called electrons. And every atom has them. But electrons cannot move through water. They can jump onto other molecules or atoms. And if they do that, we then get a negatively charged particle, which we call an ion. In fact, we call it an anion. That's a negatively charged ion. And that's exactly what we have in this water. But of course, we have to have some positively charged particles too. So whenever that electron escapes from wherever it came from, if it's moving into that water, it has to jump onto some particle. But we have to take another electron away from some other particle and make it positively charged. So we have equal numbers of positive and negative charges in that water. The positive particles or charges are called cations, and we have some of both, or some of each, in that solution, and that's why there's a little bit of electricity passing through there. But what if we had more ions? We could have more electricity, right? So let's look at salt water. This is salt water that I dipped out of our bay, and I've put some into this glass here. There. Well, there's a lot more ions in that salt water. There we go. A lot more ions in that salt water than there was in the tap water that I was showing you first. And those ions, of course, are from sodium chloride. That's salt, right? We have a positive ion, which is sodium. We have a negative ion, which is chloride. And we've got lots of them, and that's why plenty of electricity is flowing through here. So let's celebrate. All right, we're getting ready for Halloween. Now, sodium chloride is made of those two ions, and they stick together in the solid. The crystals of salt contain sodium ions and chloride ions, but they can't move. They're stuck together. When we dissolve sodium chloride in water, the ions separate, and now they're free to move in the water. In fact, they're sticking to the water instead of to each other, and that's why we have current going through here. Now let's look at some other possibilities. I've got two more chemicals here, ammonia and vinegar. And I'm going to start with ammonia. And let me say, if you want to try this at home, make sure you have a parent or another adult helping you handle the ammonia, because it's pretty stinky stuff and it can really sting. I'm going to move my electrodes onto my third glass here, the one that's labeled ammonia. Now again, there's hardly any light going on here, hardly any current going through that pure water. Well, it's tap water. It's not quite pure, but close enough. Let's add some ammonia. Now we have more ions. Clearly ammonia contains some ions. It's also pretty smelly stuff. I can smell it. So there's a lot more ions there than we had in salt water, than we had in pure water. But the salt water, I would say, contains yet more. But we have some ions, no question. Now what about vinegar? Again, we're starting with pure water, or tap water, which is almost pure water and has very few ions. Not much current. Let's add some vinegar. Well, we got some ions out into that solution, didn't we? Now, vinegar is an acid, which means it releases H plus ions. It turns out that's what we mean by an acid in water. But vinegar is a weak acid. If it was a strong acid, we'd have lots of ions and lots of electricity going through here. But instead, we have only a little bit. And it was the same story with the ammonia. It's a base, in fact, but it's not reacting with the water very strongly, and so there's only a few ions in there. But we have a base, and maybe we could do a reaction with this acid, and we might see something different. Let's find out. Oh yeah, we just made some more ions. That was a chemical reaction. What was that chemical reaction? Well, we have our acid, acetic acid. It can release this H plus ion, which jumps onto the ammonia and makes an ion, which we call ammonium ion, NH4 plus. Now that has to leave a negative ion behind because we took an H plus away. And that ion, the negative ion, we call it acetate ion. And if I was talking to my chemistry class, my introductory course, we would be talking about the conjugate base that's left behind when the H plus ion is released. So there's our demonstration. Hope you enjoyed it. I'm going to post this on our website, and maybe you'll try something like this at home. And you can send us the link and we'll post it if we like what we see. But don't forget your safety goggles. Thanks very much for listening, and hope to see you again.